So our next speaker is Jacob Bourjaily, Penn State, and he's going to be telling us about loop amplitudes, phenomenology, polemics, prospects for it.
Thank you very much for this opportunity. It's great to be back in Princeton and to spend time with old friends and make new ones. The story I want to tell today is motivated by a few big questions and from a kind of a bird's eye view. What are the kinds of functions, numbers, what special functions arise out of perturbative calculations in quantum field theory? And related to that is a theme of why has it been so hard to learn what we have learned so far. And we've seen in this conference so far, and we've learned in the last decade or two, that there's remarkable structure in this kinds of functions, the cluster algebra structure, and at the level of the integrand or the rational functions going in. And one of the themes that of this talk, or what I'd like to try to emphasize, is that by better understanding these rational structures, the loop integrand will help us go farther and to really understand the whole picture in this broader class of somewhat scary functions. But the other goal is just to introduce you to some of the things that arise in perturbative quantum field theory. So with that kind of motivation, the basic thing you need to know about quantum field theory is that there is a loop expansion. That for any observable or observable-like quantity, whether it's a number or a function or anything like that in a quantum field theory, we teach our students that there's a loop expansion if it's perturbative. And at each order L, you sum Feynman diagrams and you do some D times L integral. And so the work of a quantum field theorist is really just two parts. First, you sum all the diagrams, and then you do all of the integrals. Well, yeah, good luck. This will roughly outline the two main parts of this talk, these two things. But one of the things is that these two problems and the difficulties in both we've seen a lot more progress on summing Feynman diagrams than doing the integrals, but everything we've learned about the summing of the Feynman diagrams, or what we might call the integrands, has been informed by and helped inform the much harder problem still of doing the integrals and getting these things into some sort of transcendental functions. Now, what part of that difficulty, although by no means all of the difficulty, is related to a little subtlety which doesn't come up very much, or at least we try to ignore as long as we possibly can, which is that oftentimes, including me, physicists are overly comfortable talking about things that are not really observables, like a scattering amplitude in n equals 4. Anything with fixed multiplicity involving massless particles is not strictly observable, but it's closely related to something observable. And so sometimes these things, sometimes this integral is strictly ill-defined without some sort of regularization, or it's a few steps removed from an actual observable. But it turns out to be a very good idea to try your very best to calculate something that is observable in terms of integrals that don't diverge, if you can. Okay, so I want to just start with some phenomenology. Look through the literature and see what you find. The first thing is that this d times L dimensional integral you have to do, whatever it is, if there's a spherically symmetric part, which gives you pi to the ceiling d times L over 2, times some object. We usually ignore this pi, by the way. And we talk about some object with bounded weight, at most d times L over 2. What kinds of things come out of these integrals? A lot of observables, maybe because they're the simplest conceivable ones, like anomalous dimensions and all the kinds of numbers that we can get out of quantum field theory, simpler than functions. We can easily just scour the literature and see what numbers people have calculated. One of the most famous numbers in quantum field theory is the gyromagnetic ratio of the electron, and through two loops, we see some unusual, we see zeta 2, log 2, zeta 3, log 2. And it's worthwhile to just pause and comment on how valuable it is that we have names for these numbers. So zeta 3 is the third polylogarithm evaluated at 1, and I'm sure everyone knows that everyone in this room knows that zeta 2 is pi squared over 6, and the even zeta values are pi to some n. And when I was an undergrad, my advisor told me that pi was a dimensional quantity and you should keep track of powers of pi. And so we might assign these things weight, a zeta of n, a weight of n in some sort of sense. But I want to be cautious about that because I know that I don't want to rely on the Hodge conjecture or anything. But of course, having a name for it means that I can put it in the computer and get as many digits out as I'd like, as quickly as I'd like. But it's worth bearing in mind that deep down in the computer, this number is defined as a series expansion, or it's defined as an integral, as a particular evaluation of a particular transcendental function, which just happens to have a name. I mention that because it turns out to be really hard to give names to these numbers. Laporta and Remedy in 1996 did this, got to infinite precision. We'd call this infinite precision. And the weirdest number you see is the fourth polylogarithm evaluated at 1/2. But more recently, he tried very hard to get this at 4 loops and computed some diagrams to tens of thousands of digits. Why? Because he wanted to reverse identify this long series. In the published paper, he gives more than 1,000 digits. Why? Because he'd like to identify this particular number as some combination of these named numbers. And now it's been a few years, and we all understand now that there are some numbers that he saw that arise at 4 loops that don't have names. We should probably call them Laporta's number. Give them a symbol. In maybe QED is not your favorite theory. What about scalar field theories? Very familiar. And conveniently, for this question that I'm asking, Oliver Schnetz has a paper, Numbers and Functions, quantum field theory. And he outlines all of the particular numbers, number theoretic things that come out of massless phi-4 theory, from in the beta function, and all the things you could possibly care about in phi-4 theory. And you see there are zeta values. There's some more complicated things here, which he expands. I mean, these are pretty ugly looking numbers. But what I really want to emphasize here is that actually this comment, this list is not complete at 8-loop order. Again, yeah. What about planar maximum supersymmetry? One of the simplest things you can calculate is a cusp anomalous dimension for 2-to-2 scattering. And here, I think everybody will agree, these are beautiful numbers, at least. This, at every order, you have a sum of products of zeta values, with integer coefficients, a sum, if you properly normalize the thing. And this goes on to all orders. So this is clearly very beautiful. And moreover, if you look at every term, all these products, 3 plus 5 is 8, 4 times 4 is, or 4 plus 4 is 8. Everything has fixed transcendental weight. And this is one of the reasons why people expected that in terms of this inequality, that maximum supersymmetry in the planar limit would have this beautiful property that it would be maximally transcendental, that it would saturate this bound, unlike the gyromagnetic ratio, unlike phi-4 theory, but it would really do it. And this is closely related to an idea called that the amplitudes would be determined by their leading singularities. Now, I believe both of these statements are true, but only if you take a slightly more generous understanding of what transcendental means and what leading singularity means. And in particular, 1997, Kontsevich conjectured that at least in phi-4 theory, I think it was a restricted conjecture, but that those numbers would be of mixed Tate type, and Brown and Schnetz in 2011 proved that that would imply that they would be multi-zeta values all the way down. They showed that in the same paper where they found a counterexample. A K3 in phi-4 is what it is. So one of the morals is that there are dragons, and maybe this is a better picture for those kinds of dragons. Come back to that. But what kinds of functions? As soon as you start asking about functions, I mean, maybe it's easier to notice a good function from a bad function than a good number from, I don't know. But anyway, we're talking about a much bigger class of things that depend on many variables, and how pretty it looks can really depend on how you present it. But in general, we expect, or we have expected, that this object, whatever you do, is got some kinematic dependence, some algebraic on-shell function, and some pure function of transcendental, of some weight. And in case of maximum supersymmetry, that it would saturate this. Now, one thing you can say in complete generality is that at one loop, in any quantum field theory, in any number of dimensions, with ever masses, it doesn't matter. Everything at one loop in any theory is polylogs. So that is definitely the first thing you encounter, and it's always there at every loop. There's always a loop, which is a polylog. But what about beyond that? For a long time, polylogs were all of the examples we knew, but it might have been a bit of the drunkard looking for his keys underneath the lamppost. And, you know, the police officer asks, "Did you lose your keys here?" And he said, "No, I lost it in the park, but this is the only place where there's light." I mean, it was said another way. There are you could look through the literature and you would find integrals that people had done and they were polylogs, and integrals that they could not do and they said couldn't do. So there were polylogs and ones who knows. And one of the things we've been learning is all of that space of the who knows stuff. But in terms of these algebraic on-shell functions, I'm actually not going to define it precisely for you, but in terms of this audience, it's on-shell functions. These are all in massless series in 4 dimensions. They correspond to certain volumes in the Grassmannian with a volume form that depends on the theory, but not the geometry in particular. So you can define these things, and it's long been known that this data of on-shell functions, or at least things that are defined in this way, whether or not they're algebraic, do suffice to reproduce perturbation theory. And this is a very general correspondence for massless theories in 4 dimensions, but in the case of planar theories with maximum supersymmetry, maximum super Yang-Mills, the theory is beautifully combinatoric, and we have a lot more to say about this kind of correspondence. But even in this theory, where we think we have a beautiful description of all of these on-shell diagrams and things, there is a question: do these diagrams suffice? Are the results of doing loop integrals of perturbation theory, do the list of functions that we can easily categorize, do that span the space? So algebraic, and it turns out we now know that's not true, or at least not these things here. I mean, they still have a Grassmannian geometry interpretation, but they're an integral over some non-algebraic cycle, some algebraic variety defined in the Grassmannian. So for example, this diagram here, this is in a 13-dimensional cell in G310, and if you compute this on-shell function, it has lots of simple poles, and those simple poles correspond to factorizations of these corners. There's 24 of them. Each of those things have a positroid interpretation. Great. However, there's an additional 2 contours you can take around an elliptic cycle. And those things, I don't know how to name them. I don't know how to count them or anything, but you absolutely need them for the physics. And from a physics point of view, these are Yangian invariant. They're the right things. But after you've imposed the delta functions. So, but just on the question of these algebraic things, and also following up, it was great to follow Lauren. I wanted to point out a conjecture which she's actually helped to identify, and I also want to thank Conversations with Pasha. These are 2 numbers that I do not know. I don't know any formula for them, but they're easy to compute by brute force, which is the total number of MK dimensional cells in the Grassmannian, but weighted by the number of isolated points in the intersection with a generic n-m plane in m dimensions. So this is, what I mean by that is that if you try to put in 4 dimensions, you put all these particles on shell, there's actually 1,028 different solutions to those on-shell conditions. There's only one permutation labeling this positroid, but I'm not just putting 1 here for this picture because there's a solution. I'm putting all 2 to the 10th ones. So in addition, we've known for a long time that in addition to the positroid labels, we also need this discrete data of which solution you took if there was more than one. That's just the answer for this one. It's one of the reasons why we put it on the cover. It's real pretty, has lots of symmetry. It's a 40 particle process. There isn't an easy answer for that, but you can just ask your computer to find the solutions, which actually I don't think would work on most people's computers, but. So this is something like the number of discrete algebraic things, so not elliptic, not worse, normal things that I would need to know to reproduce an amplitude. And what's important or worth noting here is that I've exhaustively surveyed this data, and I have no idea what this number is. I don't know. I can't identify it in the OEIS, nothing. It doesn't mean it doesn't exist, but I definitely don't know this. Another number I don't know is how many independent relations there are among those functions. algebraic relations that are coming from a homology of a higher dimensional cell. But the difference between the total number of functions and their relations is something like the homology, and it's the number of independent algebraic leading singularities. And this, this is a conjecture from a lot of data, is given by this very simple formula, which happens to be ABC for A, B, and C. In particular, this is counting the number of tiles in the 8-dimensional amplituhedron. Yeah, I don't know. Yeah, this is well. So if you put m equals 4 here, that's the number of independent superfunctions, which includes all of these algebraic junk, is counting the number of tiles in the 8-dimensional amplituhedron, which is really interesting. But that's all I have to say about it because I don't understand why that is. But this is what the numbers look like here. I have found no patterns. So actually what took me forever to recognize this was the fact that I needed to include the multiple solutions. Otherwise, I didn't see any patterns. Okay. So going back to our main theme, so we have these 2 steps, and for many, many years, I mean, and hopefully, well, and for the near future at least, the hardest part has been, I mean, and maybe it's the hardest part because we have made such tremendous progress in understanding the sum of Feynman diagrams. And anyway, today, the bottleneck in almost every calculation is doing the integrals, getting from these rational understanding to some sort of transcendental, the kinds of functions that ultimately emerge. And to understand why, before I get into the details here, I want to just kind of pause and point out why this is such a hard problem, why physicists have such a hard time, even when you don't have regularization or divergences or anything like that to care about. So what's wrong, or why is it so hard? And you can get a textbook that will tell you how to do Feynman integrals. And what you will learn is that nobody knows how to do this integral. It's a bunch of quadratic forms in L, and it's just over some space. And even if it's finite, nobody knows how to do this integral. You can't Monte Carlo it on your computer. It's too high dimension. And so the first trick we teach our students in every quantum field theory class is you introduce Feynman parameters that turns this product in the denominator into a sum. And a sum of quadratic forms is a quadratic form. Very nice. And so that means that you can shift the origin and make it spherically symmetric, and you can eliminate stuff. And so you introduce Feynman parameters. You make it a bigger integral to make this integral trivial. And then you convert it into an integral over Feynman parameters. Okay, where these have a nice graph polynomial. There's a nice graph interpretation of these things, but it doesn't really matter. The next thing you learn is that nobody knows how to do these integrals either. Okay, this is over a simplex in in real projective space of dimension edge -1. Yeah, unless you're very lucky, nobody knows how to do those integrals either. So, but then you get these textbooks and you start learning some things, and suppose you have relatively few scales. So this denominator here is just a sum of things that are monomials, monomials in the kinematics. And if you have very few kinematics, you might be interested in a series expansion in those kinematics or whatever. And so you learn that even though you can't do this integral, there's another trick you can do, which is introduce Mellon-Barnes parameters. And this is based on this kind of identity here, which is that 1 over a plus b to the n is equal to this contour integral in the complex plane, which looks pretty bad, by the way, right? Is going from -infinity to -I infinity to +I infinity along here. And with the 2 pi I there, this is just a sum of residues. And if you just you close the contour to the right or to the left, you get this series expansion for a over b or b over a. So it's a funny way of writing that. But if you're thinking about how do you numerically integrate something terrible like this, this is an integral which over the domain of this contour converges very rapidly. And so you learn how to introduce Mellon-Barnes, and you get an integral of dimension. How many integrals do you have to do? It's how many kinematic monomials you have here, which for most of the integrals I care about means it's absolutely hopeless. But for an enormous number of real-world physically important problems, such as renormalization or 2-to-2 scatter, very low kinematics, very low processes, which come up a lot in real-world applications of amplitudes. So when the number of kinematic degrees of freedom is extremely small, this is a bounded integral of a size of this integral is bounded for all loop orders, and it converges very rapidly. So if you're lucky. So you introduce, oh, and by the way, I didn't point out, but this using Barnes lemmas will let you trivialize the alphas and trade it for the z integrals. Okay, and you hope for good numeric convergence on this thing. Now, I hope you all appreciate that at no stage did anybody do an integral, right? You found an integral you couldn't do, you traded it for another integral you couldn't do, and then you traded it for another integral you couldn't do. Maybe in the hopes, I mean, what's the payout of all this map? You get something where you can get digits out relatively quickly on a supercomputer. Not very much understanding. Let's look at what this looks like in a few concrete examples, and everything I'm going to talk about is finite here. So the scalar box integral in 5-4 theory, it's also just the space-time correlation function, the tree-level correlation function in 5-4 theory. Very simple integral, shouldn't be that hard. We introduce Feynman parameters, and we get a 3-dimensional integral. And one of those integrals is obviously trivial, so we can actually write it as a 2-dimensional integral. And this proportionality is here because there's a non-conformal prefactor, but otherwise it's a function of 2 conformal cross ratios here. Nice 2-dimensional integral with 2 rational factors down there, but it's a degree 2 in the alphas and a degree 1. I didn't write this projectively, but in degree 1 factors. Okay, now this, I don't know if you'd consider that done. But the first formula that most people would cite is saying, having done this integral is Szymanczyk's 1972, which used Mellon-Barnes, that transformation, and wrote as a 2-dimensional integral in the complex plane, U and V. Very easy to get series expansions out of this. And you get relatively good convergence in various places. But I think the formula that most of us remember is due to Hodges in 1977. And you find that it's got a little prefactor here with a square root in it, and then it's just a bunch of dilogs and logs. Now, I want to actually, the reason why I'm reviewing this story is because I want you to pause and ask yourself, which is the integral? The integral. Because I want to remind you that dilogarithm is defined as an integral or a series expansion. This is a series expansion or an integral. This is a symbol, which means integral or series expansion. Just because it has a name doesn't mean you've really done it. Or have you? Well, one reason why I think I prefer this bottom expression over the others is that the analytic continuation is very clear. The branch cut structure is very clear. I understand this class of functions on a deeper and better level than the other ones. And that isn't a strong reason to prefer these things, but it's some reason. We're going to come back to this. But if in the interest of just finding out what comes out of perturbation theory, we can actually continue this. And we're going to rapidly run into functions that have no names. So at 2 loops, you have this kind of picture. You can write it as a 4-dimensional integral over Feynman parameters. These are 3 rational functions of the Feynman parameters, and the integrals over the RP3, or simplex and RP3. If you can do 3 of the 4 integrals pretty easily, and you get trilogarithms, and you get an integral over an elliptic curve with a trilogarithm. So people call this thing an elliptic trilogarithm. If you go to 3 loops, you can do the same exercise, and you get a 6-dimensional rational integral with 4 factors in the denominator. And again, you can do actually 4 of the 6 integrals. And what you find is that you have an elliptically fibered K3 surface, and the volume form, the holomorphic volume form of an elliptically fibered K3 with quadrilogs. These things do not have names. And I do not know their branch cuts. I don't know the analytic continuation. I don't know the analytic properties of these functions, and they don't have names. I can easily get digits out of them, by the way. I'll come back to that. Well, yeah, pretty quickly. These are pretty convergent integrals. Li4 is very good, and a 2-dimensional Monte Carlo is great. So like Laporta didn't actually recognize he had a Clabiau in the game. He called it a multiply elliptic integral. It didn't stop him from getting tens of thousands of digits. But if you go to L loops, what you find is an elliptically fibered Clabiau L-1 fold with some polylogarithms attached. This is a class of functions that is scary, that we don't understand the analytic structure. We don't know the relations between these functions. We don't know symbology. We don't know any of the things that we'd like to know, which is a big barrier to understanding this class of functions. But I, for one, would bet that there's cluster structure in there. There's a lot of interesting structure. So what do we actually see? We see polylogarithms, yes, but we also see some kind of Calabi-Yau periods or something like that. And it turns out that actually it's not that hard to find Feynman integrals, especially when you don't consider specific numbers, but functions. This 2-point function, which are in a massive theory in 2 dimensions, at L loops, you have a Calabi-Yau L-1 fold. An elliptic integral or elliptic curve is in a Calabi-Yau 1-fold. And this is, by the way, this Calabi-Yau 3-fold is exactly what contributes to gyromagnetic ratio at 4 loops, and this is why it doesn't have a name, because it's the volume of some particular Calabi-Yau at a very special point. It's a singular point in kinematic space. Can easily calculate it, but we don't have a name for it. If you want to look at vacuum graphs, so if you're looking for just the beta functions or the anomalous dimensions in phi-4 theory, the first contribution you get is at 8 loops, and this was specifically found as a counterexample to Konsevich's conjecture. But if you look for functions, you start seeing them all over the place. And at the 8-point or the 10-point function, this whole series is Calabi-Yau 1-fold, 2-fold, 3-fold. But if you want to find things, but remember that at L loops, any one of the loops is a polylog. And so the furthest you could possibly be from polylog is 1 loop away. And indeed, in 4 dimensions, non-planar things, even with fixed numbers of external particles, can be maximally distant from polylog. So at 2 loops, you know that you have a dialog, because there's always 1 loop that's a dialog. But there's a Calabi-Yau 2-fold. At 3 loops, you get a Calabi-Yau 4-fold, et cetera. And my friends, or my collaborators and I found a lot of, got really good at finding examples of these terrible things. Doesn't mean I understand them at all. And I think it would safe to say that outside of an extremely limited and certainly the most phenomenologically valuable and the most interesting, perhaps, list of very special examples, almost all observables in almost all quantum field theories are not polylogs. So it's a very limited, narrow class, even though they're the most important to us. And what's important to me, if it turned out that we needed to understand the integrals over arbitrary algebraic varieties, I'd give up. I would give up hope really quickly. But the good news is that so far, every example anybody's ever found of a non-polylogarithmic integral involves the same kind of geometry. It's not even all Calabi-Yaus. If it were Calabi-Yaus, I'd be, it's okay. I mean, that's a pretty big category of spaces. But it's even better than that. It is just the simplest. Like, it's not what Calabi-Yau 3-folds do we see? We see the quintic hypersurface. That's it. It's the baby one that you encounter that's useless for string theory, has way too many families. So it's not good for compactifying string theory on, but it is what we see in these Feynman integrals. And this is what we always see. Now, someday somebody might come up with another example, and I don't know. But at least as long as the space of geometries that I have to care about as a physicist is bounded, I'm optimistic that somebody might come along and understand it. Unfortunately, when we learned this, we thought we were excited because physicists know a lot about Calabi-Yaus. But mostly because of the way that they've been relevant to physicists in the past, very few people have done anything on these very singular Calabi-Yaus. So they're interested in just counting how many cycles there are or something. But these things are extremely singular. They have a lot of shrunk cycles. They're not full rank. And we do not know how to calculate these things or characterize them or identify them or anything. Okay. Back to these 2 easy steps. So in the rest, I want to outline what we've learned about summing the Feynman diagrams, because we've definitely, ignoring this problem of doing loop integrals has paid off enormously, and has taught us a lot. And we've actually learned that from motivations by the difficulty of doing integrals, which I kind of want to review for you. But the goal is, at least the goal of my research is to improve this whole picture by better understanding the integrand level structure, because I think it encodes everything we could possibly care about. Okay. Now, in terms of the loop integrands, I think the most powerful approach that we have, at least in terms of getting very high orders very quickly on a computer, say, is the all-loop recursion relations, in which every single picture that emerges from this corresponds to a particular tiling, I shouldn't say triangulation, of the amplituhedron. And this provides a nice geometry, and it's something that we understand very well. recently, Simone and I implemented this pretty efficiently, and on my laptop in a couple seconds, I can get an 8.4 loop amplitude pretty quickly. So at least in the theories for which all loop recursion is known how it works, this has been the most powerful tool for getting the right answer for summing all the Feynman diagrams. But it's not necessarily the easiest, and I want to kind of clarify why. So this is kind of like a mixed understanding. It's more like in the positive Grassmannian than in the amplituhedron. But if one way of seeing what comes out is that every single term is a 4 times k plus L form over a space with 4k constraints. So this is like the original form, beautiful D-log form with some simple constraints involving the external kinematics. And we can do the 4k delta function, or do 4k of the integrals to get rid of 4k of the delta functions. You're left over with a little Jacobian here. And for when k equals 0 for the MHV amplitudes, there's nothing to do, and we're just left over with this beautiful D-log form. But more generally, we have this Jacobian, which can introduce all sorts of things, an algebraic structure, not necessarily rational. And if we can change the variables from the alphas to the real loop momenta that we have to integrate over, we get a kind of general integrand like this. And there are a couple problems with this. And I'm not sure if they're deep problems. I really don't know if I think they're deep problems, but they're certainly obstructions to making sense of this today. And that is that, first of all, the denominators here can involve arbitrarily high degree polynomials in L. Even at 6.1 loop NMHV, the first example I think we ever calculated, or that let's make a second example, you have the difference of products of propagators, or of inverse propagators down here. Now, the problem with this is that because of that factor, I can't use Feynman parameters. I can't use Feynman's trick. I'm not doing Monte Carlo on it. No, I don't. Even when I know this amplitude is finite, I can't do this integral. So all of the methods that we have for converting this term in the recursion to a particular transcendental function doesn't seem to work. There's another structural problem here, which is that there's loop dependence in the eta coefficients, which means that different bosonic components of your superfunction have different integrals to do. And so it doesn't necessarily commute with supersymmetry in a nice way. Doing the integral is not very compatible with manifesting supersymmetry. Now, that doesn't mean that I still hope that sometime in the near future somebody will come along and I'm ready to believe that this is by far, that integral d log is as good of a symbol for a special function as there can be. And whether or not I can get numbers out of it is a separate question, but I think that this might be the closest thing to understanding it. But today, we don't really know how to make any use of it in terms of comparing things. And I want to illustrate also another aspect of this, which is kind of worth noting. There's the gold standard calculation maybe is 2 to 2 scattering in planar n equals 4. It's the simplest integrand we could possibly calculate. And in many ways, it encodes everything else about all S matrices in this theory. So it's the simplest thing to do. And one thing that's worth pointing out is that it is dramatically more concise than the Feynman expansion. So we have 3 times 10 to the 28 at 11 loops. The number of BCFW cells is 2 times 10 to the 14. So a factor of 10 to the 14 better. One thing that's worth pointing out that is very interesting to me and it hasn't been very widely explored is that the number of BCFW cells in a tiling for the L-loop amplituhedron is a beautiful combinatorial number at 1 loop. And beyond 1 loop, it depends on your scheme. So this number 10 is like this is the smallest number I can find. Actually, it's not, but it's order the smallest number I can find. So this is like these numbers depend on scheme, so they're not really as combinatorial as you might like. Okay, but some of you know that this has also been a long calculated in other ways, and in particular, these numbers are not that competitive, maybe compared to what people did in the earlier days. Like at 2 loops, most people, it's a single integral plus its images, and so the number of master local integrals you would write down at 11 loops would be 651 million, which is a factor of 10 to the 6, a million times better than what you have for the BCFW cells. But as I think Song might mention tomorrow, he recently, and his collaborators recently computed the 11-loop 4-point amplitude using F graphs, these correlation functions, and it's a mere 2 million terms. 2 million is still a big number, but it's definitely handleable on my laptop. Whereas 3 times 10 to the 28 is not. And you might wonder, why are there so many more terms? And this is probably, I could easily see myself in the very near future turning this on its head, in the sense that what is the reason why there are more terms in the recursion relations is because every single term is exposing a very specific sequence of cuts. So in particular, like this particular term in the recursion relations here corresponds to this pathway through this graph. Different pathways correspond to different terms. Whereas the local integral of this topology has all of the pathways in it at once. And so it's a little bit like the symbol. It's capturing every single iterated sequence of cuts you could possibly take. And that is probably exposing exactly the structure that I want. And so it's spelling it out in gory detail, and I probably want that. But this is why a local integral like this, which supports many, many, many different sequences of residues, it captures 1 million times, or 1 million different terms in the BCFW recursion relations. Okay. Now, what many people maybe don't know in this, depending on where you're coming from, is the history of these on-shell diagrams actually emerged not from integrands or even tree amplitudes, but from the problem of doing the integrals. The integrals are so hard that you don't want to do any integrals that you don't absolutely have to. And it was noted by Passerino and Veltman in the late 70s that at one loop, at least, in d dimensions, you can take any Feynman graph. This is a graph level statement. You could expand it as an integral into a sum of integrals with fewer than most d propagators. And that means that if you care about a d-dimensional theory, you can truncate this list, do this list of integrals, tabulate it in your appendix, and you're done. And now the only problem is finding these coefficients. Now, what is this? Why does this work? It works because this is a basis for cohomology, right? The integrand is a rational function on the space of loop momenta. It's an element of cohomology. And so if you write down all differential forms, a basis for differential forms, modulo integration by parts, you can construct these coefficients as by what they call projection or reduction, modulo IBPs. And it breaks my heart to say this, but at the LHC, people do this diagram by diagram. They literally take a Feynman diagram, project it into a basis. They're usually satisfied by that. No, not me. What was noted early on and what kind of gave birth to this modern revolution that we're in right now, or what's going on in our understanding of on-shell physics, the origins of these pictures were from Byrne, Dixon, Kossauer, and Dunbar, where they recognized that actually you don't need to look at Feynman graphs to talk about these coefficients. In fact, all you need to do is think about cuts. So if you took this, say, unitarity cut of the loop integrand, so don't do an integral over all of loop momenta, but just do it on a contour that puts these particles on shell, then you break up a one-loop graph into trees. And you can keep going and construct these coefficients directly in terms of on-shell diagrams or on-shell functions. And this allows you to construct them in a gauge invariant way. And it is remarkable to remember that all of this work, there was 10 years of really interesting work involving these pictures before a single person knew how to compute a tree well. Before the tree level recursions existed. But the point is that these functions appeared as solutions to this kind of basis reduction problem. And it's pretty clear that this works completely generally at any kind of loop order. So what I mean by that is that you can construct, if you have a basis for cohomology, unitarity tells you that you can fix these coefficients in a gauge invariant on-shell way in terms of on-shell functions by first finding a spanning set of elements of homology, cycles on which this period matrix is full rank. And then on every one of these cycles, you know what the amplitude is because it's an on-shell function. It doesn't require gauge redundancy or anything else. And so from this data, your knowledge about on-shell functions and this period matrix of your basis, you can just do linear algebra to find that the coefficient here is just Ci is just the HA, the on-shell functions times this inverse matrix here. Now, one of the things that we've learned relative to what people knew long ago is that it is not possible, or rather, the space at, say, 10 points, 2 loops, or in non-planar 8 points, 2 loops, this period matrix, in order for it to be full rank, necessitates cycles that are not polylogarithmic, that do not encircle simple poles. And I don't have a better language for describing that, but you need to include these elliptic contours or complete integrals over integral middle dimensional cycles of a Clabiow k-fold. You need those in general. But once you have this period matrix, you know the data, you can invert it, you find these things. And this is how generalized unitarity can be used to find these coefficients directly. Okay. To illustrate how this game works, and how, you might recall this Park-Taylor amplitude, which has a beautiful interpretation in terms of the Grassmannian. This is the top dimensional volume form on G2n, where G2n is are the space of lambda spinners. But at tree level and at loop level, one of the first applications of these ideas of generalized unitarity was to show that at one loop you could reproduce, you can capture this entirely in terms of boxes. So the no triangle hypothesis. And this guided a lot of people going further. But to go to higher loops, you need to have a complete basis, and it gets more complicated than just scalar boxes, triangles, and whatever. And the heroic feat for 2 loops was first done by Christian Vergu, where he wrote down a big enough basis, found all the coefficients, and his answer was just, he has these basic integrals in his basis, and these are the algebraic coefficients, and they're kind of involved, 12 pages. Actually, I think before this paper came out, shortly after this paper came out, within 6 months, my collaborators and I here, Nima and Freddie and Yara, guessed this formula and checked it. How did we check it? It's because in the intervening time, we had the recursion relations. So it's very easy to check that we had the right answer. We had the right answer. We knew the right answer, so we could guess it and check it. And since we found this, it's been a compelling suggestion that maybe this is a good way to write the answer. And in fact, we also pushed our intuition a bit by going to 3 loops and also checking that this agreed with the, and to this day, this is the only 3-loop closed formula expression for all multiplicity that exists, so it's pretty remarkable. But I want to emphasize that these formulas were guessed, they were checked against the right answer. And what's happened in the intervening years is that we now understand this is now science. We can construct this cleanly. And the basic philosophy is that instead of taking a stupid basis and computing this period matrix, choose your basis to be the cohomological duals of a spanning set of cycles. Choose your cycles first. And by making them the duals, the period matrix is the identity, and now you're just matching cuts directly with individual integrals. And it turns out that these integrals are very, very nice and allow you to write these kinds of formulas in great generality. For any renormalizable quantum field theory, you can just write down a clean basis and write this down. And it's guaranteed that these will be the best integrals by standards that are used today. I'm going to come back to that in a second. Okay. So there's still a question about, so what I hope you can appreciate from this. Not exactly canonical. I want to say any spanning set of cuts will correspond to epsilon canonical integrals, but there are better choices. And there are some choices are much better than others. There's still a lot. Absolutely. And that's what I want to end on is explaining the art, I guess. So the first thing is that once you know that you can expand into a basis, whenever anybody expands something into a basis, you should be wary that if they chose the basis poorly, their coefficients will be terrible. And the beauty of the answer is going to depend a lot on how you chose your basis. And a crappy basis is crappy. The most common choice of basis, and there are good technical reasons for this, by the way, but it's also the first guess you might make, which is, let's just take a scalar Feynman graph and analytically continue the exponent on every propagator, nu, put no numerator in there. If you want a numerator, you can just take a negative exponent there. And one reason why this is a good space is because it's actually relatively easy to compute the dimension of this cohomology. It's also a general theorem that this object is meromorphic in epsilon and the nus, and that it only has simple poles at integer values of epsilons and nu. So it's and moreover, it's very easy to project into this basis using Laporta's algorithm. So this is in everybody's code, and because it's in everybody's code, it is this crappy basis is an intermediate step of almost every practical calculation. And I can qualify that if you're interested later, but it's suffice it to say that everybody knows these are crappy integrals, meaning they do not satisfy nice differential equations. They have linear combinations of polylogarithms, elliptic polylogarithms, and higher all at the same time. They're just big mixtures of crap. There's nothing nice about these integrals, even though they happen to be the first ones you might guess, beyond one loop. And even at one loop, I'd say they're crap, but that's more private. So, and in fact, it is definitely true, everyone would agree, that these integrals are so terrible that none of them can be integrated. So who cares that you can expand into this basis if you can't do a single one of those integrals? But one of the general, let's just step back. One of the moral lessons of generalized unitarity is that you can pick your basis. So, moreover, this has nothing to do with the quantum field theory in question. Meaning that if you find a Feynman integral-like thing, an element of cohomology, a thing, whether it's coming from a Feynman graph in a particular theory or not, if you find something nice, it is a potential basis element in any basis. So why not populate our basis of master integrals of this thing with the best conceivable integrals that are the nicest ones? And it also allows you to focus your attention not on an amplitude or on this whole big problem that is very difficult, but what is a good integral? What makes an integral good versus bad? And one of the things that another lesson that everybody agrees on here is that this integral is almost perfect. Not quite. And the reason is because of the stupid square root that depends on u and v. Now, the square root depending on u and v means that when I hit this thing, that this part here, which just has no algebraic prefactors, is a pure polylogarithm. I define pure in a second here. A pure is a function which, when you hit it with the derivative, goes down to something of strictly lower weight. And in the case of polylogarithms, what I mean by this is that the space of nth polylogarithms, if you differentiate them, you get a linear combination of n minus 1th polylogarithms. And if you hit a d on a log, you get a rational function. In contrast to a function times a log, which has the product rule in it. So this thing has a piece which maintains the weight, and then a piece which goes down in weight. And it was the insight. So if you renormalize this, or if you rescale this integral, then you get something pure, and this satisfies a beautiful differential equation. And since certainly pioneered and and pushed forward by Johannes Henn and others, it has been realized for a long time that constructing integrals that have this property, this is a property that you want. You want to find integrals that are pure in this sense. And I'm going to make that a little sharper in a second here. But there are still things that are not satisfactory about, well, I'll come back to that. Okay, so a canonical basis, and this is in the Johannes Henn sense, is what people search for now when they are looking for integrals, is they want to construct a system. They want to have a big set list of integrals, and they want to organize them, and they actually solve this by brute force to have this property, that when you hit, that there's a grading by something that we're going to just define as weight, and there's a subspace of weight w, w minus 1, w minus 2, et cetera. And then when you hit a differential on the w, anything in the w strata, you go to something strictly lower in the strata. So if you have a basis that is organized in this way, we call it that satisfies nilpotent differential equations, then we call the thing at level w its weight. And that exactly agrees with transcendental weight, but I think it actually generalizes much better. I'm always scared of what Francis Brown will tell me when I talk about weights, but this is at least self-contained and is clean. So something that is graded in this way deserves to be called weight. And one of the things that Johannes Henn really emphasized is that as soon as you have a system of differential equations like this, it is very easy to numerically integrate this up iteratively as one-fold integrals. And one-fold integrals are so easy to Monte Carlo that for the sake of getting digits out, you've done the integral. So this is better than all of the other previous ones, in terms of getting from expressions to numbers. But the problem, and this is going back to what Nima was asking about, is that purity alone is extremely weak. Any linear combination of pure integrals with constant coefficients is pure. It doesn't really mean that it exposes anything of interest or that they're nice integrals. And in particular, in the case of the one loop, say, scalar boxes, bubbles, triangles, or triangles and bubbles, one sense in which that is a crappy choice is that when I hit this integral here, once I've normalized it correctly, is conformal and finite. And yet, in everybody's favorite basis at one loop, the logarithms, the weight one things, are spanned by bubbles, which every one of which is UV divergent and not conformal. Why on earth would you put non-conformal divergent integrals in your, say that the derivative of my beautiful finite function is a linear combination of terrible things? You shouldn't. And it turns out to pay off if you don't. So even at one loop, where in any number of dimensions, every scalar integral that people would ever write down is so close to being okay that everybody just tolerates it, because it's proportional to something. There's an overall prefactor that if you just normalize it correctly, it's pure, and everybody's satisfied then. This is unnecessarily divergent. And what I mean by this is, like, at 7 points, every single box integral you write down is infrared divergent. And yet, every one of those infrared divergences can be entirely removed by just subtracting off subtriangles and find a finite integral. It's not conformal anymore, but it's finite. And similarly, bubble differences. You don't need a regulator for the difference of bubbles. This is an exercise in any good quantum field theory textbook. This is basically what Pauli Villars does for regularization. The difference of two bubbles, you do not need to regulate either one of those two. This difference is perfectly finite, and it's log. It's a beautiful function. And why would you write down divergent integrals in your basis when you could just have differences and have them finite? And in fact, if you want to get rid of as many divergent things as you possibly can, to illustrate this is what people usually do now. If you look at 7 points, you'll have 3 massive triangles that are finite. Every one of your boxes is divergent. All the other triangles are divergent. All your bubbles are either UV and IR or UV divergent. But you can construct a basis where almost all the integrals, all of the boxes, and the infrared divergences here matter, and there's only one element in the entire basis that is UV divergent and not IR divergent. This little element bothers me. It's just a massless bubble. So it depends whether or not you care about wave function normalization. Anyway, the point is that you can easily arrange your basis so there's only one thing in the entire list, which is ultraviolet divergent. And when you rotate, if you just take anybody's answer and rotate it into this basis, where there's only one element that's UV divergent, the coefficient of that divergence is a tree. And the coefficient of every infrared divergence is a tree. And everything else is perfectly finite. And it tells you that if you want to compute a finite observable, you don't need to regulate anything. So why are we tolerating all of these divergences throughout our basis, sprinkled everywhere through it? It's because maybe it's because we weren't trained to expect anything nice to come out of it. But now that we know that there are nice things, we should organize our calculation as much as possible so that when I ask a finite question, I can do it in terms of steps which are finite without introducing fake divergences. And I think we can do this according to lots of different gradings. And so far, we've had a lot of success in finding as refined a category as you could possibly want. So what I mean by this is, can I organize my basis, not just by weight? Weight's good. That's a good starting point. You should do that for sure. But can you organize it so that there is a finite part and a divergent part? And it's important that that division have the property that no linear combination of divergent crap is finite. As soon as that's true, then everything that's finite will be it must have coefficient 0 on that subspace. But moreover, you can divide it by UV divergent and infrared divergent. You can even organize it at higher loops. You can order it by how divergent it is, by the degree of divergence, and separate off the space according to how divergent it is. And in every one of those strata, this is completely recursive. I mean, this is very nested. Whether on the divergent integrals or the finite integrals, you can divide that space of finite integrals or divergent integrals by maximal transcendental weight, next to maximal weight, all the way down to rationals. And you can divide it up by polylogs, elliptic polylogs, K3 polylogs, and you can fully separate it. And so while a scalar pentabox integral might have 4 elliptic curves inside of it and a polylogarithmic piece. If you put this in a larger basis, you can see that it is a linear combination of 4 integrals that deserve to be called pure elliptic polylogs, and 1 integral which deserves to be called a pure polylog. And so you can fully separate out this different geometric structure into an individual integral capturing a single one of these geometric objects. And I'm not sure if that's always possible. It's actually, there are reasons to be skeptical. For example, the space of all of master integrals is not large enough to saturate the homology of a non-singular K3 at 2 loops, like the 2-loop non-planar 8-point amplitude or diagram. There's no master integral space that could possibly do that if I needed to span all the 22 cycles. The good news is that it's singular, but it's now a detailed question about whether or not you can divide out. Can you identify a specific differential form for every single the co-cycle attached to every one of the cycles, every independent cycle? And that answer is not known. So I don't know if this can continue, but so far we've been able to. And I want to end this talk with just this big picture, what I think is great about and why it's exciting to be in doing scattering amplitudes. And it's perpetually like this. It's this virtuous cycle where somebody computes something extremely difficult. And usually, whether it's in a real theory or imaginary or just because they can, doesn't matter. You calculate it. And then maybe they or somebody else discovers something incredibly simple. And then you scratch your head and you try to understand it. But once you understand why, you can build it into tools. Like for example, Del Duca, Duran, Smirnov calculated the 2-loop remainder function for 6 particles heroically, 18-page formula at the final answer. And Anastasia and her collaborators found it, shrunk it down to 1 line. It took about 2 to 3 years before people understood that structure and started guessing things. And then Lance built it into a big giant tool, machine, and got it up to 7 loops. And we discovered all sorts of structure. And he's not doing integrals either, right? He's really just getting the answer from the structure that we've discovered inside of this thing. And that is the hope, is that we can maybe skip all of these, or there isn't much of a distinction between integral and a symbol that means integral. And so I'm optimistic that we can really understand these functions by at the integrand level and can capture everything we do care about. I'm including numbers for experiments someday. But anyway, thank you very much.
All right, we have time maybe for one quick question.
I have a quick, I have a long question, but a quick question. So, do you think it's fair to say that saying you've solved an integral, or just to come to that point? So if we find the differential equation in the A matrix, and you put it in the nicest form you like, that sounds close to qualifying as having solved it, except for the general question I don't know the answer to. If you give me the differential equation, do we really know how to get a series expansion for the answer everywhere? Or, I mean, in simpler cases that we learned in school, you can have the differential equation and that gives you a series expansion around some points, but there's some art to figuring out how to expand around infinity, other places, figure out where all the branch cuts are, blah, blah, blah. And often that art goes back to the integral representation with some contour deformation and so on. So is there some, do you have a picture, or is there a picture, is there a canonical picture for, given the differential equation, that you essentially do know, in principle, how to get the series expansion around every point, put it on the computer, et cetera?
That is a fantastic question. So it also goes back to why I might prefer one of the functions versus the other, is that when I write down dilogarithm, I know where its branch cuts are. I know how to take a monodromy. I know everything about that analytic structure.
Or someone told us. I mean, someone did some work to do that.
Yeah. And I'm tempted to say that we don't know how to in general. Other than different kinematic, different places in different branches, you'd have different boundary conditions, and then you could just integrate it up. But that's not the same level of understanding that we have. Like analytic continuation is a much more powerful idea for these kinds of functions than just I can throw it on my computer and get a number out of it at every point. And I mean, Hofi and Sebastian have done a lot of work on thinking about this. If I'm just isolated it to an analytic function of these symbols S and stuff, do I really know the branch structure? And I don't think we do, even if I can solve the differential equations quickly.
For questions in the lunch break. So just to remind everybody, the lunch for us opens at 1 o'clock.